In this video, we are going to discuss velocity time graph. So for velocity time graph, we'll be plotting on the y-axis the x component of velocity or the y component of velocity depending on whether you are moving in the x direction or the y direction. So that's for the y-axis. For the x-axis, you'll be plotting time, so this will be the time axis. Okay, so what kind of situation we'll be using to sketch our velocity time graph? So we'll be using the same situation that we have been discussing in the acceleration and the displacement time graph video. So you have a person standing at the origin, starts to speed up towards a jog, then a run, then maintain the same speed until the 6th second, then starts to slow down to a stop at the 8th second. Okay, so this is an example that we've been analyzing quite a lot, but now I'm going to add on a second portion of the journey. So it means by at the 8th second, after it comes to a stop, it will continue its journey by starting to go back towards the negative direction, okay, or goes in the opposite direction. So once it comes to a stop, then it makes a U-turn. Technically, it makes a U-turn. Then it starts to speed up. But now it's speed up in the opposite direction. So from a jog to a run. After that, slows down to a jog. Then stop at the origin, the same place where it starts, the initial position. So this is the situation that we are going to be analyzing. So we are going to plot this graph here. So it's x component of velocity against time. Okay, so let's make the diagram simpler. We remove the body just to make everything simple. Okay, so now to plot the velocity time graph, we know that we are going to be plotting the x component of velocity. So if the x component of velocity is larger, that means it has a greater speed, right? Okay, no matter it's going in the positive region, positive 5 is greater than positive 3. Means that you are moving a greater speed. Okay, 5 meter per second is greater than 3 meter per second. So greater speed up here, lower speed down here. How about this side? This side also means the same thing. If it's a negative region, negative 3 and negative 5, what's the difference? Negative 5 is still faster than negative 3. Okay, it's just that negative means it's moving in the negative direction. So if I say negative 5 meter per second, it means it's moving at 5 meter per second towards the negative direction. So negative 3 will be 3 meter per second in the negative direction. The negative and positive here represents the direction. Okay, so if you see here, right, in my diagram over here, I've labeled each dot here with a vector arrow. Actually, this vector arrow here is actually representing the velocity vector, where the direction of this vector arrow here is representing the direction of velocity. So as you can see, if the object is moving to the right, then my direction of velocity will be pointing to the right. Because for instantaneous velocity, the direction of the velocity vector is equivalent to the direction of motion. I move to the left, my direction of velocity is to the left. I move to the right, the direction of velocity will be pointing to the right. It follows the direction of motion. Okay, so that's for direction. On the opposite side, you can see it's pointing to the left. That means this object here or this person here is moving to the left. Therefore, its direction of velocity is pointing to the left as well. Okay, so that's direction. And with that, right, we can actually know if the object or the person here is having a direction of velocity that is pointing to the right, that means it is moving in the positive x direction, right? If it's moving in the positive x direction, that means the x component of velocity should be positive because it's moving in the positive direction, so the x component will be positive. Whereas for the opposite side over here, it's moving in the negative x direction, so you should expect the x component of velocity to be negative. So you should expect the first portion of the journey here, it will be sketched above the time axis because the x component of velocity is positive. You should expect your sketch to be above the time axis. Whereas for the second portion of the journey, where everything is moving towards the negative x direction, you should expect the x component of velocity to be negative. Therefore, the second portion of the journey should all appear below the time axis because that's where your x component of velocity will be negative. Okay, that's for direction. For magnitude, you can see that the longer my vector arrow of velocity, that means the greater the speed that I am traveling. If you see over here, the arrow here is shorter, that means it's traveling slower. If it's a longer arrow over here, it means a greater magnitude of velocity, that means it's traveling faster. So if there's no arrow, that means the magnitude of velocity is 0, which means it is at rest. So at rest, slow, fast. So this is a speeding up process. Same length, same length, same length, same length. So this is what we call as constant speed, because it's a constant length, means by constant magnitude of velocity. Whereas this part here, the arrow is getting shorter until the arrow disappears. That means it is a slowing down process because the magnitude of velocity decreases. Okay, so over here, since it's speeding up, you should expect the x component of velocity to grow over here. Then since it's maintaining over here, you should expect it to remain constant. Then once it slows down, you should expect the x component of velocity to decrease to a 0, right? Because 0 is when it stops. Okay, so that's the idea of a velocity time graph. Whereas for the second portion of journey, you should plot a similar thing, but on the opposite side of the axis, means by below the time axis. Okay, so here's how I visualize it. Okay, this is what happens in my mind when I am thinking about a velocity time graph. What I do is I bring these arrows and I bring these arrows into the graph. Okay, this is what happened in my mind. It's not what's actually you're doing, but you can think of it like this. You can think of it as bringing the velocity vector down towards their respective time. So you can see that now you can see it's an increasing increase of speed, remaining constant speed, then slowing down to a stop. Okay, by bringing down the arrow, because the length of the arrow represents how great is the x component of velocity. Then the direction pointing upwards signifies it is in the positive x direction. So actually bringing it down, you can sort of see the shape of the graph already. Let's do that for the second part. For the second part is moving to the negative x direction. So you should expect a negative x component of velocity. So in that case, all the arrows here should be pointing downwards. Should be pointing downwards. So we bring 9 to 9, 10 to 10, 11 to 11, 12 to 12. So let's do that. Bring everything down to its respective time. And that's it. Okay, so you can sort of see the shape of the velocity time graph already. But all this thing is a bit too small. We have a large space over here. Let's lengthen our whole graph, something like this. So now you can see that the velocity time graph is actually just connecting the tip of the arrow. And here I have my velocity time graph. Okay, so how I usually think or how I usually interpret the velocity time graph is I can think of it as velocity vector for each second. So it gets longer, that means it's faster. It gets shorter, that means it's slowing down. Then it gets longer again, means by increasing speed. Same length means by constant speed. And after that, getting shorter means by decreasing speed. Then if it's above the time axis, it's moving in the positive x direction. If it's below the time axis, it's moving in the negative direction. Okay, so this is how I visualize the whole process of making a velocity time graph. And of course, let me label this. This is moving in the positive x direction if it's above the time axis. This is below the time axis, so I say moving in the negative x direction. Okay, so that's it.